in. Yes, so very soon. Uh, okay. Yeah, we are recording this event, so just to make us aware of that. And of course, if you put on your video, it means you don't mind your face showing. So, I mean, if you have a problem with that, you may want to put up your video. So, thanks a lot.
Okay,
Yes. So,
that is
just a
perfectly
minute, we can just kickstart the whole.
Smart Matters meeting.
Okay. So, my name is Emmanuel Jason Dansu. Um, I'll be co-hosting this event today with Dr. Nick Akonu. Let me see.
She's waiting to play.
She's in the background somewhere trying to do things in order. Yes, she's coming in now. All right.
For just check.
All right. Um, so maybe we definitely have some time for interaction. But I think first of all, I'd like to share the order of events before we continue. I'm trying to locate that right now. Yes. So in the chat, you'll see the order of events as we'll go about it today. Um, just like I said already, I'll be moderating alongside Dr. Nika Ihonu. So let me click on this. So just a minute. And then all right, so that's the order of events right there in the chat. So all right. Well, like you know already, this is the Black in Mathematics Association, and it's basically the a collective of Black mathematicians anywhere in the world. As far as you're a Black person, whether you're from you're of course we are all from Africa, right? Originally, but of course we have Africans all over the world. We have Black people all over the world. I mean in Asia, in Africa, of course, in Europe, everywhere not minding your nationality or whatever. As far as you're a black person, this association is for you. And basically, we are very strong on collaborations, on networking. Interestingly, just recently, one a paper as a group of people, like one of our research groups, I think about six of them, they collaborated and we had a paper published not quite long on mathematical modeling. So that is the kind of thing we are here for. Then in the past, we've done events talking about scholarships and all of that. So that is basically why we are here to make Black people come together so that we can also have our somebody said if you don't have a seat at the table, then you can create your own table. That's the kind of thing we're doing. Maybe of course some of us have access to certain tables, and of course we just need to enlarge the table so we can also have access. And especially in this when we talk about diversity, inclusion, and equity. So we all have to be to feature prominently. So without further ado, so because of course we are in different time zones, we are very conscious of our time. So I want to hand over to Dr. Nick at this point to introduce our first speaker, the speaker for the first session. Dr. Nick, over to you.
One participant is
Do we have Dr. Nick here? Okay, yes, please.
Can we mute ourselves?
Oh, okay. Maybe I'll try to mute people who. So let's mute ourselves. That'll make it faster. Okay, Dr. Nico.
Okay. Good day, everybody.
Good day to you.
Okay, good afternoon, everybody. Good evening from wherever you are joining in. I hope we can hear me.
Yes, I hear you at least.
Okay, all right. So I'm one of the facilitators for the event this evening, and I'll be taking the first session with Dr. Dansu. It's good to have all of you on board, and I welcome you gladly. I hope we have a very interactive and interesting session in these 2 hours. So our first speaker for today will be Dr. Patrick Jomegni. I hope I don't murder that name. I sincerely apologize if I've murdered that name. So Dr. Patrick is joining us. He is a senior lecturer in applied mathematics at Northwest University, South Africa. Can't pronounce that name now. Something Room campus. He has supervised 8 MSc students and 1 PhD student. He has taught several courses up to postgraduate students in South Africa, Chad, and Ethiopia. He has also served as reviewer for many peer-reviewed journals. He's been a jury member for L'Oreal UNESCO for Women in Science Fellowship Program from 2018 up to 2022 at different intervals. He's also a virtual reviewer for NRF. Dr. Patrick is the founder and leader of the 3MC, the Mathematical Modeling Mini Courses, and he has contributed to develop MSc and PhD curricula in applied mathematics in Ethiopia and Chad. He has also organized several CROMS seminars. He is a member of SIMPA, SAMS, IAMG, and the Golden Key International Honor Society. He has published 16 research articles, the recent ones being on the spread of COVID-19 in the post-lockdown era and on a meta-population model for Zika virus disease transmission dynamics between linked communities. Dr. Patrick has been a visitor, researcher, and scholar at N'Djamena University, Chad, SIMPA, France, Mathematical Biosciences Institute in USA, and the Victoria University, Canada. So it's our pleasure to have Dr. Patrick speak to us today he has research interests in mathematical epidemiology, mathematical ecology, differential equations, fractional calculus, and numerical computations. So today, he'll be talking to us about epidemiological and ecological modeling as a whole. So, we are glad to have you. You have the floor. Please go ahead and make your presentation. Thank you.
Okay, thank you very much. Can you hear me?
Yes, I can. We can.
And may you please allow me to share my screen? The host,
okay.
Can you please allow multiple sharing? I would like to thank the Black in Mathematics Associations for giving me the opportunity to interact with you and also to share some of my recent work with you. And I also want to thank Dr. Adejimi and Emmanuel for the communications. I am Patrick Chapman Jomeni at Northwest University, the Potchefstroom campus. Can you see my screen?
Yes, please.
Yes, we can see your screen.
Yes, we can see your screen.
Okay. I'm not going to discuss about ecology today because of the limited time, but I'm just going to present one of our results with my master student in Ethiopia. So I'm going to talk about an HIV/AIDS models with non-classical isolations. And of course, I acknowledge my master student, Andwalem Tekle. He's now doing his PhD. And also one of my collaborators, Dr. Mohamed Dawa, both in Ethiopia. The outline is as follows: the outline, a brief motivations, then the model formulation, the analysis, interpretation, and a brief conclusions. As we all know, AIDS is an infectious disease caused by a human immunodeficiency virus. And the HIV infected T helper lymphocyte, which is responsible to coordinate the actions of other immune systems. And to declare that you are HIV positive, your total count of CD4 plus T cells should be less than 200 millimeter per gram. Yeah. And HIV can be transmitted through sexual intercourse, we all know it, blood transfusions, contaminated sharp material, and we also have the vertical transmission mother to child. And as in 2020, when the article was published, based on the statistic, HIV through sexual intercourse account for 70% of all infections in the world. As a result, it has been declared as a sexually transmitted disease, even though it can also be transmitted through other means. And about 75 million people in 2020, they have been infected by the virus, and 35 million died since the beginning of the infections, and 37.9 million live with HIV/AIDS in 2018 worldwide, and 35 million died from the start of the infections. I already said it. And to fight the pandemic, several preventive strategies has been implemented, and one of the strategies also was to prevent the infections, and it was found that an antiretroviral therapy drug, tenofovir, could reduce the risk of HIV transmission up to 96%. So it was a drug manufactured to prevent the infections. However, the accessibility and the cost is a challenge. In Ethiopia, why Ethiopia? Because the case study was done in Ethiopia. In 2018, about 690 people were living with HIV, and 23,000 were newly infected in 2018. 11,000 people died from AIDS-related illness. 79% of people living with HIV, they knew their status, and 65% of people living with HIV were on treatment. That's why we also found important to consider the class of people who are aware of the status, and also the class of people who are using the treatment. Another important factor to consider, especially in Ethiopia, is that HIV/AIDS is affecting the performance and the productivity of labor force dependent organizations. Why? Because most of infected staff, they took unauthorized time off or medical absence. And in this case, less experienced worker replace experienced disease worker, and this also affects the productivity. The deterioration of the physical aptitude also leads to low productivity. I can share with you some picture in Ethiopia. So here we have people farming. You could see how important the labor force is. And also this is in Indonesia. We also have another factory. And when the staff are not physically fit, it also affects the productivity. So the main question that we try to solve is to slow down the spread of HIV infection and ensure maximum productivity. As we all know, those who are infected, they perform less in terms of labor work. And we also don't want to promote recruitment based on the serology status. So our model is more inclusive in the sense that we advise those organizations not to recruit based on the serology status because it's not even allowed by the law, but to see how they can maximize their productivity. And in this case, we propose to classify the workers into two categories. There's what we call the isolated and the non-isolated. And by isolation, we mean the set of non-infected individuals who freely accept to reveal their status, and they take a commitment to keep their status as long as they belong to the organizations. So we propose to the management to classify the worker into two classes. We have those who freely accept to reveal the status and to keep their serology status as long as they belong to the organizations. And you have the second class, the non-isolated. So non-isolated are either those who are infected or not, but they don't want to reveal their status. And we believe that investing on the isolated workers can guarantee the stability. Why? Because at least we know that they are not infected, and investing on them can guarantee the stability and can also maximize the profitability. And we propose to the management a special benefit to those people. It could be fast promotions, it could be special allowances, and also more tasks to do. So the aim here was to investigate the impact of isolated class on the transmission dynamic of the infections, and also to study some strategy to keep the infection low. Here is the mathematical model that we proposed. We consider a population, we subdivide the population into 7 compartments. We have the susceptible, we have the susceptible who are aware of the preventive measure. We have the isolated, those who are accepted to be isolated, and they are aware of the preventive measure to avoid the infections, like the use of the ART drugs, or the use of the proper use of condoms, or also the practice monogamy. We have infected, and we have also another class IP. These are infected who were aware of the prophylaxis measure, but they have been infected due to the efficacy failure of the prophylaxis. For example, it's not everyone who uses condom who is 100% safe. So some might use condom and still get the infections, or some might use even the antiretroviral and still get infected. Remember that the study shows that only 96% of people who use the drugs are saved. So we still have also another proportion of 4%. We have the class of 8. So here in this model, we assume that a proportion of susceptible of the prophylaxis measure, they join this class, And among those who are aware, some now are using the prophylactic measure. And among those who are using the prophylactic measure, only a proportion sigma is safe. So the remaining proportions can be infected. They will join the IP class, and then the states can get worse, and they move from being HIV infected to AIDS individuals. The remaining proportion who is not aware of the prophylaxis measure, when exposed, they can be infected. They will join the I class, and if they don't follow a proper treatment, yes, please. And if they don't follow a proper treatment, they will join the 8th class. We also have H1, the class of those who are isolated, not using the PrEP. And you have H2, the class of those who are isolated using the prophylaxis measure. Here are our governing differential equations. And the main idea here is to understand the dynamics in the population, and also to study the strategy to reduce the infection, to keep low infections. Of course, looking at these mathematical models, provided initial conditions, the model is well posed in the sense of ADAMA. And we can also show that the solution of our system, the solution is positive, and the solution is also bounded. It's not a problem. Now we compute the disease, the equilibrium point. So we have two equilibrium points. One we call the disease-free equilibrium, and the other one we call the endemic equilibrium. Then we compute also the basic reproduction number. And the basis of reproduction number here represents the average number of infected individuals infected by a single infectious when he is introduced in a population of purely susceptible. Then we have this result that you have proved. We prove that provided R1 less than this and R0 less than 1, therefore we can have a disease-free populations. The disease-free equilibrium was locally and globally stable. So this information tells us that to ensure a population free of the infection over time, we need to keep R0 less than 1. And the next question is, what are the strategies to keep R0 as small as possible? It's possible using a sensitivity analysis. We look at the rate of change of R0 with respect to the model's parameters. For instance, we observe that the rate of change of R0 with respect to H1 and H2 is negative. It means that to decrease R0, we can increase the isolation rate. So the more we encourage people to join the isolated classes, the lower will be the secondary infection. So we will have less infections. This is one strategy, is to encourage people to join the isolated classes. And one of the means of encouragement is to provide a goods package that will attract them. We also notice that when H1 tends to infinity, secondary infection will be 0. And when H2 tends to infinity, secondary infection will not be equal to 0. In the first case, it means that if all the susceptibles are isolated, there will be no secondary infections. But if only those who are aware of the prophylaxis measure isolate, will still have some infection in the population. We also look at the impact of the efficacy and the awareness of the prophylaxis measure on R0, and we realize that to reduce R0, one can also increase the efficacy of the PrEP. So here we need to invest on the treatment and the drugs that we use to prevent the infection should be more effective. We also notice, we also observe that even if we increase the awareness, even if the whole population is aware of the infections, we can still have secondary infection to increase. But the awareness has an impact only when this condition is satisfied. The awareness, therefore, increasing on the awareness could reduce secondary infection. Otherwise, investing on awareness through public campaign and so on will have no effect. We also realize that if the drugs is 100% effective only, we will still have secondary infection. Why? Because not everyone is aware. But if we invest only on awareness and the whole population is aware of the infection, we still have secondary infection because they are not using the drugs. But if we combine both, 100% awareness and 100% efficacy, therefore secondary infection will tend to zero. This is the ideal situation, but it is very costly to invest on public campaign, making the whole population aware, and also distributing the antiretroviral therapy drugs freely to them, and ensuring that they are 100% effective. So this is the ideal situations. We also look at the impact of the contact rates on R0. We realize that to decrease R0, we can decrease the contact rate. So one of the strategies is to restrict the contact rate, the sexual contact between infected and susceptible. The implementation is very difficult because we have to enter into the privacy of people. And it's very difficult, but it's a strategy. And if all the contacts, when all the contacts reduce it to zero, we will have a population free of infection over time. These are the ideal situations, but not easy to implement in reality. Now we use the data from Ethiopia to determine the best strategy. Because using the absolute sensitivity, we only have the different scenario, but what is the best scenario? So using the data, what do we observe here? We observe that if we increase the awareness to 10%, therefore the number of secondary infection will decrease to 31%. And if we increase the efficacy of the drug to 10%, the secondary infection will decrease to 25%. Likewise, if we increase the isolation rate or we decrease the sexual contact, this is the impact on secondary infection. So based on this scenario, we could see that investing on awareness is the best strategy. Is the best strategy to reduce secondary infections. Just to summarize what we said, the best strategy to reduce secondary infections based on the data that we got on Ethiopia is to invest on both high awareness and also high efficacy. Of course, it's costly. Or if we consider the case of low awareness and low efficacy, the best strategy to reduce R0 is to either decrease the sexual contact or to isolate more individuals. And here we have to enter into the privacy of people. And when we have low efficacy, the best strategy is to invest on isolation. So through our model, we could measure the impact of each parameters on the whole dynamic in the systems. We have some simulations. Here we have the case of disease-free, because here this is the infected compartment. So over time, all the infected population will converge to 0, and then the population will be disease-free. This is the case where our disease-free equilibrium is stable. So R0 is less than 1. And we also have another scenario, the case of the endemic. We have low awareness, low efficacy. We have an endemic situations where the disease will live forever in the populations. Yeah. Now we try to look at the impact of awareness. So we could see how the awareness reduces the infection. As we increase the awareness level, secondary infection also reduce in the populations. And here we also have the impact of isolations. As we isolate more people, there will be also less infection in the populations. So to summarize here, I didn't plan to enter into the technicality because I assume that not everyone is familiar with this thing. So the main idea here was to show you how we use mathematics to address an issue in Ethiopia. It was really a burden on the Ethiopian government because most of the industry rely on labor force organizations, and HIV has become a burden to those organizations. So now the question that we try to answer, or the model that we try to propose to the management, is to assist them not to recruit based on the serology status. So we want to avoid discrimination, but we help them to maximize the productivity of the organization. And maximizing the productivity of the organization is maximizing on healthy individuals who freely accept to rebuild their status and to maintain their status. And to those people, we propose also a special package. And through our model, our numerical simulation or our mathematical result, we could see the impact of the isolations or the impact of awareness and the impact of the efficacy of the drugs on the dynamic of the infections. So we recommend to limit the secondary infection. We recommend to either invest on awareness, but high awareness, or to invest on the efficacy of PrEP use. But here it needs to invest also on research to manufacture effective drugs to prevent the infection, or at the level of the organizations, we does not necessarily need investment on research, is to invest on isolation, is to bring a package that will attract people to discipline themselves for the organization to be highly productive. So having the largest possible number of isolated individuals can guarantee low infection and a disease-free population over time. And so this special class of worker in industry can also be applied at a university environment. We can call it a special status of lecture. It can be applied in many organizations whose productivity depends on human labor force. The challenge that we face here is that we consider a linear force of infection due to the complexity of the mathematical analysis. And we already submitted a paper where we defined an optimal control problems, and the aim was to minimize also the cost of the infection. because we have the strategy. For each strategy also has a cost. Now we try to look at the optimal cost that can also ensure low infection and also an optimal productivity of the organizations. And yeah, so this is the masterwork of my master student in Ethiopia, and the work was published, and the work has been quite well cited so far. Thank you so much for your attentions, and I will be glad to receive questions or comments.
Okay, thank you very much, Dr. Patrick. Thank you for sharing your knowledge with us. And we are going to take some questions now. First of all, I'll start by saying, for those asking for the recording, Dr. Kayode has answered you. The recording will be available at the end, and the link will be sent. Once we are done, we will send the link to the group so that you can now access the recording. Then if you want to ask questions, kindly just raise your hand. You'll be called upon to speak. And when you are called upon to speak, please just go straight to the point. Don't start thanking the speaker and commending him. We'll do all that later. Just go straight to the point so that you can maximize time. All right, so the floor is open for those who want to ask questions. We have limited time to do that. Yusuf Zubair, your hand has been up. Do you want to ask a question?
Yes, ma'am.
Mr. Yusuf Zubair, okay, please unmute yourself and ask.
Okay, my question is on the reproduction number. Now, the reproduction number is one of the most sensitive parameters that can actually determine whether the disease is going to be continue to spread or actually control the spread of the disease. Now, is all the parameters, all the variables in the model, can the basic reproduction number cover all the models? And if not so, does it mean that it's only the parameters that appear in the basic reproduction number that actually contribute to the control of the disease? That's my question.
Okay, thank you, Mr. Yusuf. Dr. Patrick, you may wish to respond to that.
Okay, thank you, Yusuf, for your questions. I think the basic reproduction number here contains, it's a very good question, but I think it contains almost all the parameters. Now, if ever there's one parameter in the model that is not in the basic reproduction number, it simply means that the parameter does not have an influence on secondary infection. Why? Because if you compute the derivative of the basic reproduction number with respect to that parameter, it is zero, because the basic reproduction number doesn't depend on the parameter. And when it is zero, it means that the parameter does not influence secondary infections. Yeah, so it does not influence the dynamics of the infections. But in our case, I think all the parameters are represented in the basic reproduction number. So they do play a specific role.
Okay, thank you, Dr. Patrick. Dr. Yusuf, I hope your question has been answered. I'll call on Dr. Ataribu Samuel. Please go ahead and ask your question.
Okay, thank you very much. The data collected, as in the data evaluated in the model, first of all, I saw the I thought, I want to know the method they use. It's a disease I know that is quite intrinsic to people to open up and give out if they are positive or negative. So which method of data collection was adopted for the collection of data and the analysis as well? If you can put more light, I'll be grateful. Thank you very much, ma'am.
Okay. Dr. Patrick, will you want to answer one after the other, or they should ask everything at the same time?
It's up to you. I have no problem. You decide.
Okay, let's just take this one. Okay, you can respond to this one.
Okay, I think there was a network problem. I don't know if his question is on data.
Yes, he was asking how the data was collected, since it's difficult for people to tell you their HIV status. They want to know how the data was collected and the analysis that was done, how you went about it. So you just summarize for him.
Okay, okay. Prior to this work, there was also a work that was done by an Ethiopian, but he was studying at the University of KwaZulu-Natal in South Africa. So he got some funding and he collected some data, and we use also his data for most of the parameters. The data was already available because it was part of his thesis, and the only parameter that we estimate are gamma, sigma, H1 and H2. We just estimate these are the level of awareness. They are between 0 and 1. So in the case that we have 50%, if 50% of the population is aware, we consider gamma equal to 0.5, and we see the impact. On the transmission dynamic. So this is just a continuity of a work that was done with some epidemiologists here in South Africa.
All right. Thank you, Dr. Patrick.
And for those who are interested in data collection and model fitting, we are organizing an African mathematical school in mathematical biology here in Purchase Room from the 20th of March to the 28th of March. I will share the link with you. So there will be speakers from Canada, 4 of them, and we'll have a series of lectures on data collection, data fitting, and so on. So from raw data, and from your data, what is also the model selection? Which type of model is recommended to fit your data? Okay. So there will be a course on it in 2 weeks here in South Africa.
Okay. Thank you, Dr. Patrick.
Pleasure.
So I believe you share that with us, and then we'll share it to the ledger audience, and those who are interested will join in. Okay, we have just a few minutes left to round up this session. So I'm just going to, we just have 2 more hands up. So I'll call the 2 of them to present their questions, and then you answer the 2 questions at the same time. Okay, so first is Dr. Lubem. After Dr. Lubem, Simon Ad will ask his question, and then we take the answers at the same time. So Dr. Lubem, you have the floor. Please make it snappy.
All right, thank you very much. Dr. Patrick, I don't know, in Africa, it is very difficult to get data that you are sure of. That's you get exact and accurate data.
Oh.
It's very difficult. And I don't know what are the measures that you have taken to ensure that this work actually is close to reality of what is happening in Ethiopia in terms of HIV.
Okay, thank you, Dr. Lubem. That's noted. Let's take the second question. Simon Ad, please unmute yourself and ask your question.
Thank you so much. I wish to know, is this webinar only for mathematicians, or other related disciplines can also be participants? And then my second question is there a particular number of data collected, or just collected it randomly to an extent and then you stop? That is my question.
Okay, thank you. And Bala Yusuf, you are the last person. Bala Yusuf, please unmute yourself. Bala Yusuf.
Good day.
We can't hear you. I can't hear you.
Okay.
Okay, go ahead.
Hello.
Yeah, go ahead.
All right. I want to ask a question regarding the topic. HIV/AIDS model, non-classical isolation. So I want to ask whether this isolation means the person that are infected with HIV should be isolated in a certain location so they can be tested. That's what we're thinking about. Thank you.
Mr. Bala Yusuf, I can't hear you well, but I think I heard the word isolated. I don't know if you're referring to the isolated class. Okay, your network is breaking. I don't know if it's just me or every other person. I can't hear you well.
Oh,
Could you
we can
type
hear
your
you.
question in the
Thank you.
chat?
Yeah,
Maybe you can type it in the chat since I can't hear you well.
Okay.
All right, thank you. So, Dr. Patrick, could you kindly respond to the other two questions? Dr.
Okay.
Lubem was asking about the integrity of the data collected, and then Simon had asked about the quantity of data that was collected, if there's a limit.
I think in my previous response, I said that on this work, we do not focus on the data first. Secondly, our numerical simulation were only for illustration purpose. Because from an analytic point of view or from a theoretical point of view, we try to understand the dynamics. From a theoretical point of view, we assess the impact of each parameter on the dynamics by looking at the absolute sensitivity. Yeah. So the simulation was just to give to illustrate the theoretical result. Now we took our data from a work that was already done on HIV, the case of Ethiopia, to illustrate what could happen in this scenario. We do not necessarily claim that it is the exact scenario, because each data that is collected, we implement our theoretical results, you will arrive to the same conclusion, So the simulation here was for illustration purpose. We did a theoretical analysis, and from the theoretical analysis, we could get recommendations from the theoretical analysis. Now, the data collection, as I said, this was a master thesis work, so we did not focus on data collections. Now, for those who are interested in data collection and fitting into the model and so on, if you have a very good a very good background in statistics, you can do interpolations. Or I could also recommend a course that will be taught in 2 weeks on data collection, data fitting, and model selection. In the presentation of today, we are not talking about the data. It was just some theoretical work and the illustration based on a data that we collected from the literature.
Okay, thank you, Dr. Patrick. Bala Yusuf has typed in his question. His question said, I'm asking about the isolation in the model. Was it referring to keeping the infected persons with HIV/AIDS in a particular place for treatment? That's his question. And I think I can answer that. That's not the idea. He explained at the beginning what the isolated class referred to. So I think probably you joined in after he did that introduction. So you would have to watch the replay to see how he groups the population into the isolated and the non-isolated class. Doesn't necessarily refer to those that were kept because they had the challenge of HIV. And I think for this session, that will be all for this session, because we have 2 other people waiting to speak to us. So thank you, Dr. Patrick, for your time. I hope you will still be on standby till the end, because some other people would have to, might want to ask questions at the end of everything. So just do well to stand by and join us to listen to other speakers. Thank you, everybody. So we'll go ahead to listen to the second speaker now. That session will be chaired by my co-host, Dr. Dansu. Dr. Dansu, over to you. You have the floor.
Yeah, thank you so much, Dr. Nika. Thank you so much, Dr. Patrick Jomeni. We are very grateful for that insightful talk. Yes, just a few announcements before we take the next speaker. I know a lot of people are interested in the recordings of this event. I want to inform you that we are recording, and then by the time it's all ready to be uploaded on YouTube, and the link will be shared to everyone who registered. So so you have nothing to worry about. So you can always go over these things. Yes, of course, I want to acknowledge our convener for Black in Math Association, Dr. Adejimi Adenuji. You know, he likes to hide, he likes to work from the background. He's doing a lot of things in the background. And of course, I acknowledge Dr. Kayode Oshinobi. He's a bulldozer, always moving and shaking things. Yeah. Then, of course, if you're interested in getting the certificate, having participated in this program, feel very free to um, send your name and affiliation to the email address that I'll be sharing in the chat right now. I'm doing that right away. So if you want a certificate, having participated in this, so you just send your name and affiliation to blackinmathematics at gmail.com. So now at this point, we've had a very nice talk already from Dr. Patrick Jomeni. So we're going to have our next speaker, and I'm going to introduce her to you. She's definitely going to have a nice time listening to her. She's Dr. Josephine Tete, and she's a postdoctoral researcher at the Frankfurt Institute for Advanced Studies, FIS, in Germany. Originally from Accra, Ghana, she holds a BSc in Mathematics and Statistics degree from the University of Cape Coast, Ghana, and an MSc degree in Mathematics from Stellenbosch University, South Africa. Doing a PhD at the Johann Wolfgang Goethe Institute, Frankfurt. Nine, Josephine studied the mathematical modeling of resistant infections between hosts and within hosts. She's particularly interested in using mathematical models and computational tools to study real-world biological problems, especially in healthcare. She also has a keen interest in mentoring young scientists. So please make welcome Dr. Josephine Tete as she talks to us about infectious disease or any topic of her choice.
Okay, thank you so much for the introduction. I think I'll share my screen quickly and then proceed. Okay. Okay, can you see my screen?
Yes.
Yes, please.
Can you hear me?
Yes, we can.
Yes, we can see.
All right, thank you. Okay, so first of all, thank you so much to, sorry, thank you so much to the organizers for inviting me. And I think we are going to have an interesting time today. And thank you everyone who joined us well to listen to me speaking today. So as he mentioned in the introduction, I will talk about infectious disease modeling. And my name is Josephine, and I'm a postdoc at FIAS in Frankfurt, Germany. So quickly about the outline. So I will start to talk a bit about what mathematical modeling is and why we need it. And then before delving into what infectious disease modeling is, and then I'll give an example of a model that I did on COVID, and then give a short conclusion. So let's start first with what mathematical modeling is and why do we need it. So mathematical modeling is basically a tool that allows researchers or allows scientists to represent complex systems using mathematical equations. And by representing these complex systems this way, we can analyze them using mathematical tools. We can use that to make predictions and also know how the model will react to changes in various inputs or parameters. So some tools that we use here include differential equations, a bit of statistics, Monte Carlo as well. And as I go on with the talk, you see some of these tools being used. So using mathematical modeling, basically it runs in somehow a cycle, which can be summarized or summarized into 4 main processes. So first of all, you need to identify what the problem is that you want to solve. And then you formulate a mathematical model from this problem. So you define your variables and your parameters, you make assumptions, and then now you can select an appropriate mathematical framework. After that, now you have your model. What do you do with it? So you analyze this model, you solve the mathematical model that you have using some techniques from mathematics, and which is also why one of the good reasons why mathematical models are necessary. So after this analysis, you achieve a mathematical solution, and you can interpret this solution into a practical solution. So with the practical solution, now you verify with your initial problem to see if the solution you have is accurate, and you compare the predictions to the real world problem that you started with. So if after doing this for the first time and you realize that there are some differences, or the solution that you arrived at does not match exactly to your problem, you can change your parameters, or you can redo your model and go over this cycle again. So the choice select a good and a fitting model to your question, to your problem. And then also if you are using data, you need to select also the model that will be suitable to the data that you have. So as I mentioned, every model is developed for a specific purpose, and it should be used only for that purpose. That's something to keep in mind whenever you are modeling using mathematics. So now, what about infectious disease models? So infectious disease models are basically a type of mathematical model somehow that focuses mainly on the spread and control of infectious diseases. So with infectious disease modeling, we typically use mathematical equations to describe the dynamics of disease transmission, and also to investigate the impact of various interventions that can, the impacts of various interventions within the population. So as I mentioned, it's a process of using mathematical models to understand and predict the spread of infectious diseases. And this process can help us to answer questions such as how quickly a disease will spread in a population, how effective will different prevention and control measures be, how many people are likely to become infected, and how many people will require medical care, and also how long will it take for the disease to peak and decline in a population. So these are all questions that infectious disease modeling helps us to answer. So there are several types, there are several kinds of infectious disease modeling models, but I have put here just 4 of them. So we have compartmental models, we have network models, and we also have agent-based models as well as data-based models. I would say data-based models are fairly new. I think with the developments of technology and the ability to be able to handle large databases, these types of models have also become very useful in recent times. So in the subsequent slides, I will talk a bit more about compartmental models as well as network models. I wouldn't go too much into details on database models and agent-based models. So let's start now with compartmental models. So basically, these are models that divide the population into different compartments based on the disease status. So either people who are susceptible or who are prone to an infection, or people who are already infected with the disease, or people who have recovered from the disease. And this is a typical example of the model that Dr. Patrick talked about in the first presentation. So where you have a population considered maybe of people who have HIV and people who are susceptible and all that. So this is a typical type of model, compartmental models that can be used to answer or to model such situations. And with such models also, we assume that the population is homogeneous and that individuals are, excuse me. Okay, we assume that the population is homogeneous and individuals are equally likely to interact. Also, movements of individuals between these compartments are determined by a set of mathematical equations, which an example of which we saw in the first talk. So these mathematical equations can be ordinary differential equations or partial differential equations. And such models are also good for qualitative forecasting. So we can use that to see how many people are going to be infected, say in a couple of weeks or days or months, or how many people are going to recover from a particular infection at a future time. So the most simplistic and popular compartmental model is the SIR model, or the susceptible infected recovered model by Kemak Baknardik in 1927. And this model basically divides the population into three. So we have susceptible, infected or infectious, and then recovered. And the movements between these different compartments are modeled as rates. So beta here represents the rates at which a susceptible person becomes infectious. And then we also have gamma, which represents the rate at which an infected person recovers from an infection. So a system like this can be represented using difference equations or differential equations. So for a typical SIR model, we have this differential equation, which is used to represent the system as shown here. And a simple simulation of this system gives us a graph like this, so where you have a number of susceptibles reducing with time, and we have the infected rising and then peaking after a couple of days of the infection and then subsequently dying out, whereas the recovered are increasing. So this is the typical and very simplistic compartmental model known as the SIR model. Another type of compartmental model is the SEIR model, which is basically an extension of the SIR model. So in this case now we have an exposed class. So the exposed individuals are in a latent period. So as we had with COVID, from the dynamics of COVID, we know that after someone is in contact with an infected person, the person goes through an infectious period, an exposed period, in which during which time that the person has the virus, but it's not yet transmitting the virus to other people. So it's not yet infectious, I would say. So that exposed period happens in exposure happens in the latent period, and the SEIR model captures this exposed period in it. And with the SEIR model as well, due to the exposure, the latency period, we can have time delayed epidemic behavior. So as well, we can represent the SEIR model this way, where you have beta, epsilon, and gamma all representing rates of movement from one compartment to the other. And we can also have the differential equation used to represent this SEIR model. So in general, we can see that compartmental models allow for any kind of model equations. We can have age-dependent equations, we can have SUIRD or SIHRDV type of model. And these all depends on how the population is divided. So on the right here, you see a model which was developed by this is having my screen. Okay, just a minute. Okay, so we have a model developed by yeah. We have a model developed by Muhammad Ali and Mehdi during the COVID-19 pandemic. And this model has about 8 different compartments, and each representing different divisions of different groups of people based on the status of disease. So we have the susceptibles, we have infected and asymptomatic, we have the diagnosed, healed, ailing, recognized. Those are the symptomatic and infected or detected individuals. We also have threatened, who are actually symptomatic, infected and detected, and we also have extinct. So as I mentioned, with compartmental models, you have a bit of freedom that you can basically, looking at the transmission patterns of the infection you are modeling, you can be able to divide the population into different compartments and be able to study this using mathematical models. And it's worthy to note that increasing the complexity of the model does not necessarily mean that you are going to have a more precise or a better model. So that's something to keep in mind. So a bit about agent-based models. So they are also known as individual-based models. And these models simulate the behavior of individuals or people in a population and how they can interact, with each other and the environment. They are also used to study the impact of individual level interventions like vaccination, and they capture very well the heterogeneity in the population and allow for more complex interactions. They are also particularly useful in studying diseases that spread through contact or behavior. So at this moment, I would like to talk briefly about my work, a little bit of my work on COVID. So this involved, the aim of this was to explore the disease dynamics of COVID when the original strain of the virus is in circulation with a mutant strain. So these mutant strain can be Omicron, it can be Delta, or any of the other mutant variants of COVID that we had over the past couple of years. So for this model, we assumed that vaccine is effective against the original strain, but the mutant strain evades the vaccine. We also assumed that individuals who recovered from infection with the first strain are prone to reinfection with the second strain. And for our infection process, for the simulation of our model, we selected a population of 100,000 individuals, and we ran 100 stochastic simulations for each given scenario. So basically, this is a brief of the timeline of the model. So at the beginning of the infection at t equals to 0, we introduced the first variant, and then we assume that the second variant is not yet introduced or is dormant. So we have an exposed class of the first variant to be 1 at time t equals to 0. whereas the exposed for the second will be 0, obviously, because there are no, the second variant has not yet been introduced. So in a completely, in a given population where the disease or the virus has not yet been introduced or has not yet been experienced, this is very typical for that. And then after a given time, say at time t equals 220 days, we introduce now the second variant, at which point now we have a number X individuals already in the first, already exposed to the first variant. And then now we have we introduce now the second variant, where now E2 now is greater than 0. And we run with these two until time t equals to 560, and after 560 days, and then we end the simulation there. So in the next couple of slides, I will talk a little bit about the process that we went through, and then also give some results. So this is the model that we used. So we used an SEIRV model. So we have the susceptible, exposed, infected, and recovered classes for both strain 1 and then strain 2. And for our model as well, we have the rates of change of susceptibles to exposed, and then exposed with the first strain, and then exposed with the second strain. And then since it is an agent-based model, we include some probabilities, and the probability of an exposed person becoming recovered is modeled with a binomial probability, and the same goes for the probability of an exposed becoming infected. So in a nutshell, this is the model that we used, and we combined this model with a social network. So basically you have a social network where people are connected to each other, and with these people, you can have people who are already infected or people who are susceptible, and with the introduction of vaccine as well, you can have people who are vaccinated. And so the network here we see on the far right basically represents a mixture of people of the different classes, of the different compartments. So you can have a mixture of susceptibles or exposed or infected or vaccinated or recovered individuals, all within this, this network. And on a social network, using network modeling, we assume that the nodes of the network are people, and then the edges of the network represents the interactions between these people. So now talk a bit about findings. So we found that there are higher infection peaks in strain 2 relative to strain 1 for different vaccine efficacy levels. And then we realized also that for 100% efficacious vaccine, there is a plateau of very low peaks of infection. And this is reached even with a population coverage of 30%, as you can see in the figure D. So a population coverage of 30% and above, we see that there are low peaks in strain 1. And then for strain 2, that occurs at 90%. So generally, when we look here, we see that the peaks of infection are much higher for strain 2, which are the orange lines, than for strain 1, the blue lines. That's the first finding. Another finding was that when we look at the average number of cases for the different vaccine efficacies, so we've considered vaccine efficacies of 40, 60, 80, and 100%. and we considered a population coverage of 10% to 100%. And with infected cases, we realized that there is a general decline in the number of infected cases as more people are vaccinated in both strains. So what does this tell us? So vaccination tells us that vaccination, regardless of which variant it is, vaccination leads to a general decline in the number of infected cases. We also see that with the first strain, with strain 1, a vaccine efficacy of 100% ensures that there is no infection when 30% or more of the population has been vaccinated, which we see in this first figure here. At 30% population coverage, we see that the with vaccine efficacy of 100%, which is the red line, there are no red bars here, from 30% up until 100%, which tells us that when at least 30% of the population is vaccinated, at least the first strain, we are not able to find infected cases, or the average infected cases due to the first strain are almost inexistent. However, when we look at the second strain, we see that the disease still persists, infection still persists up until when 90% of the population has been vaccinated. Of course, when 100% of the population is vaccinated, and vaccination, regardless of the efficacy of the vaccine, we do not have any infections, as we can see in the two figures on the right. Also, another thing to note is that we have more infectious cases due to strain 2 than we have for strain 1, irrespective of the vaccine efficacy and then the population coverage. So a typical example here is when population coverage is like 10% in strain 2, we see that the value with a vaccine efficacy of 40%, the value is a little bit above 0.025. However, when we look at the same thing for strain 1, the value is about 0.013. So we see that there are higher infection values being obtained due to the strain 2 infections than due to strain 1 infections. Now let's look at what happens when unvaccinated people are exposed to strain 1 and to strain 2. So unvaccinated exposed decline in both with both strains, with increasing population coverage, and there are higher values again for strain 2 than for strain 1. And then we realized also that unvaccinated individuals who are exposed to strain 1, population coverage of 30% or more gives low to no exposure to the virus, which is similar to the previous slide. Now let's look what happens with vaccinated individuals. So vaccinated individuals who become exposed or asymptomatic to strain 1, we see that they are lower for strain 1 than for strain 2. And again, 100% effective vaccine yields no infection in both cases. And these numbers, these vaccinated individuals who become exposed, rise at low population coverage and peak at about 60% or 70% and decrease again at higher coverage levels for strain 1, somehow following a normal distribution, but not exactly normally distributed. Yeah. And we see also that for strain 2, the vaccinated exposed increases for vaccine efficacy of 40, 60, and 80. And then for 100% effective vaccine, it peaks at 40% of population coverage, and then starts to go down again. So in a nutshell, from our study, we see that when a vaccine resistant strain is in circulation together with the wild type of the virus in the population, we found that even with vaccination campaigns, it is possible to have infections greater than when there is no vaccine. Also, we find that more people are infected with the resistant strain or the mutant strain than the wild type, irrespective of the efficacy of the vaccine and the population coverage. And a third thing is that a vaccine which is 100% effective yields low to no infections within the initial strain or the wild type strain when 30% or more of the population is vaccinated. So this is a summary of the results or the findings from that particular work that we did. So I will conclude now. So in general, infectious disease modeling is powerful for helping us to understand transmission dynamics of infectious diseases and for informing public health policies. And as I mentioned, two commonly used approaches are compartmental models and individual-based models. And the choice of modeling such question to be answered, as well as the data that's available. And both compartmental and individual models have important strengths and limitations, and therefore it's important to know these strengths and limitations, which can then guide you to choose an appropriate model for your problem. So with this, I'd like to thank you all for your attention and welcoming any questions. Thank you.
Wow, that's serious. Thank you so much. I really like the fact that you went from the rudiments for people who are probably total novices to infectious disease modeling. Thank you so much for that. That's so interesting. So if you have questions, please feel free, raise your hand to ask your questions. Yes, I have a terrible Obuzonyi Samuel. Please go ahead. If you cannot speak, you can also type in the chat, in the chat. So please, Sam, you can go ahead, please. Great presentation indeed.
From the results, the first result shows that if I may go lower from the result, the first result shows that those who are in fact there is more of COVID when the vaccine is present.
Breaking.
And
from the sound is breaking.
Sound is breaking. Can you hear me?
Perhaps you could type it into the chat.
Maybe you should
breaking. The line is breaking.
It's breaking.
Can you hear me now?
Yes, it's fine.
Can you hear me now?
If it works.
Okay, let me go again. I said from the first result, the results from the first one, it shows that when there's a vaccine introduced, we have more cases of COVID. That is compared to when there's no vaccine, it drops. But when the result there is vaccination, we had more COVID issue or COVID-19 increase. Why the third one showed that when we have effective vaccine, there is a case of reduction of the disease. But following the SEIRV, I did not see the space that's where it comes back that somebody that has been vaccinated can also be affected. So I don't know whether that two lines are contradicting themselves. That's the first and the last result, as in the first column of the result and the last one, the summary that I saw. I don't know whether it's contradicting themselves because the vaccine, the third column showed that the vaccine will totally eradicate or probably brings to none the reproduction. But the first one said that the introduction of the vaccine as well, more increase of the COVID is there. So I don't know if there can be any little clarification in this. Thank you.
Okay. Should I go ahead to answer him?
Yes, feel free, please. Feel free. Thank you.
Okay. Okay, so maybe I start with the latter part of your question. So when I was talking about the assumptions, I mentioned that the vaccine is effective against the original strain, and then the second one, it's not. And I also mentioned that the people who recovered from infection with the first strain are also prone to reinfection with the second strain. And so when you look at the figure here, I think this was the figure you were talking about. When you look at the figure here, you see that with no vaccination, with no vaccination, which is this first point here at 0% population coverage. Of course, the for strain one, it is at around 1.238, just a little bit above 1.25. And for strain 2, we have it at a little bit above above 1% of the population. But this, I should mention that these are the mean peak of infection. So these are the numbers of the number of cases that we have at the peak of infection. What really tells us a bit about the average, the infected cases, I would say, is this one, where we have this general decreasing of the number of infected cases in both cases, in both strains. And with 100% efficacious vaccine, we see that with a population coverage of only 30%, more infections being recorded. So I don't know if that answers your question or not.
Okay, can I continue, please? If I'm permitted,
sorry, because of time, I'm sorry, you could just type it in the chat. I'll only take a DBC Paul and Dr. Nick Ahon. Because of time, we still have a speaker to go. Please. So if you have a question, you can type it in the chat. Maybe Dr. Tete can answer you, please. So, but for now, we can take a DBC Paul and Dr. Nick. Please.
Yeah, thank you. My first question is, why is that error term was not inclusive in the model used for the COVID-19? Since we all know that we are not 100% perfect, why is that error term is not inclusive, was not inclusive in the model used? Then my second question is based on what kind of data collection method was applied to get the 100,000 responded on COVID-19, like which kind of data collection method was used to get that 100,000 responded? That's my question.
Could you please come again with your first question? I couldn't get you properly.
Okay, my first question is that why is that error term was not inclusive? Error term was not inclusive in the model used. Since you know that we are not
sorry, what was not included?
Error time.
Error time. Okay. So, if I may ask, what do you mean by error time?
I think it's
error time is just
okay. All right. Sorry, please go ahead. Okay, I think the idea I got from this question is that since we are sure all models, no model is 100% accurate, that why is something like error tends to accommodate for error. included in the model.
Okay. So maybe I'll start with the second question about data collection. So this was somehow a theoretical model with with computational simulations. So when I stated that a population of 100,000 individuals and 100 stochastic simulations, so we didn't use any data from COVID as the disease was happening. We didn't use any data, but we ran some stochastic simulations to somehow run some stochastic simulations over the SERLV model to study how this dynamics will be like with time. And now with your second question, error time not included. Well, no model is perfect, I would say. And there's more room for improvement for many models. And with regards to error time, I'm not particularly clear on what you mean by that. And so I am at loss as to exactly what you are asking me. But I would say that for sure, models have limitations. And as I mentioned, it's important to use models that are more suitable to the problem being solved. Yeah.
Okay, I think on this note, we have to appreciate. Who's that? Okay, yeah. So Dr. Teta, we are very grateful for your great presentation. Thanks a lot for also doing justice to the. Oh, Dr. Nika is here, standing by for the questions. I'm sorry. Please, sorry. I think I'm in a hurry to go for us to go on to the last speaker. Dr. Nika, please.
Okay. My
Yes,
question
sorry.
is my question is very simple. Dr. Josephine, concerning the model, I saw the flow chart that you showed. I was looking forward to seeing some set of equations, okay, to capture the flow diagram or the flow chart that you displayed, but I didn't see any. And that's number one. I'm wondering, okay, an agent-based model, how is the analysis done? Because I just saw you move from the flow chart to the graphical simulations. So I think in between, I don't know, is there something you're supposed to kind of explain? Because usually for the compartmental models, you see a system of equations and then we go ahead to analyze them. So this one, is it that it doesn't have any system of equations, or it has, but it just kept it for time?
Okay,
and again, sorry, just last one. This one now you're saying, okay, when you want to study something that has to do with the behavior of an individual, or just to an individual based activity as regards that model. But I know that even in compartment models, you could also still study things like vaccination, as you're saying here. You can still study the impact of vaccination and all the rest of them, even in compartment models. So why do you have to really do an agent-based model? That's what I want to clarify.
Okay.
Thank you.
Okay, so you're right. With compartmental models, you can still have the division or the compartment for vaccinated individuals, but the little or the slight difference between compartmental and agent-based models is the fact that with the agent-based or the individual-based model, you can focus on individuals within a network of the population. So basically you have a network, an underlying social network, which denotes the individuals, and then you have the edges, which are the interactions between these individuals. So with compartmental models, you don't look at the network, you don't look at somehow the interaction between individuals within the network or within the population, But with agent-based, you look specifically at those specific interactions between the people. It can also be somehow about the movement of the people within the population. So whether people are traveling or people are staying indoors, or so things like that. You can look at that on an individual basis, something that you can do with a compartmental model. So that is somehow what allows us to be able to somehow characterize individuals based on different characteristics that we can use agent-based models to achieve. So I hope that answers your question.
So you don't have a system of equations to analyze?
Oh, yes. So the system of equations, for the sake of time, I didn't show that slide, but we basically have, like I showed in the flowchart, so we basically have movements from one class to another, or from one disease status to another, not necessarily having system of equations as you saw in the first presentation. So we have movements between susceptibles to exposed, for example, and with that you can go ahead to do your individual based model. I can refer you to the paper or the initial paper for this. This is a continuation of one paper, so I can refer you to that paper, and you can see very well how the structure of the model is. You would realize that it's not really based on differential equations as you saw in the previous one.
All right, thank you. I think I will check that out and then get back to you. Thank you.
Okay.
Okay, thank you so very much for the great presentation. We're very grateful for that. Okay, a few announcements still. I saw Simon Ad asking, is this webinar for mathematicians only? And my simple answer to that is, right now we're discussing mathematical modeling, and it's bordering on epidemics like COVID-19. So automatically, anybody who is interested in COVID-19, like health workers and maybe even policy makers, be interested in this. In fact, we're going to have more webinars in the future. For this year, we have about 4 webinars slated. The next one is going to be, I think, maths in finance. Another one is maths in tech. Another one is maths in society. So if you're talking about maths in finance, for instance, I know people in accounting or financial and finance generally, I mean, not even the mathematicians can be interested in that. So our activities are open to everyone who is interested in how math is related to their lives. Then somebody also asked how they can join BMA. That's with Dr. Lubem. You can join Black in Math by just click on this link, which I just shared in the chat. That's our website. So from there, you see how you can actually become a member of Black in Math Association. Without further ado, I want to move on. I want to go back to my co-moderator, Dr. Nika Hioni, to introduce our last speaker for today. It's been a very enlightening session, and I'm very sure you're going to have another big one. All right, Dr. Nika.
Okay, thank you, Dr. Dansu. Good evening once again, everybody. I hope you all are having a great time. So you can just drop your favorite emoji in the chat box just to tell us you're still with us and that you're having fun listening to our speakers and learning one or two things. Just drop your favorite emoji in our chat box and we'll appreciate that. So moving on, we are calling on our third and last speaker for today. That is going to be Dr. Segun Oke. Now, this is what we call the high and mighty. Dr. Segun Oke, I was excited to see that you'll be one of the panelists today. So let me quickly introduce Dr. Segun. Dr. Segun Oke has a PhD in applied mathematics from the University of Zululand, South Africa. His MSc in mathematics is from the University of Ibadan, Nigeria, while his BTech in pure and applied mathematics was from Ladoke Akintola University of Technology, Ogbomosho in Nigeria. Dr. Shagoke is affiliated with the Department of Mathematics in Ohio University, Athens in the United States of America. He is currently a visiting professor and researcher. Dr. Shagoke has authored and co-authored multiple peer-reviewed scientific papers, and he has presented works at many national and international conferences across the globe. His contributions have received high praise from respected topic experts all across the world. See why I was saying I was excited to have him on this panel. Dr. Shagoke maintains active memberships in a number of societies and academies. Dr. K's academic career is decorated with several reputed awards and funding. He's a man of many parts, so please pay attention when he's talking. Don't even blink. Dr. Shagoke's research interests include creating quantitative models of cell-cell interactions within tumors and at the tumor-host interface that is empirically and therapeutically justified. He uses a variety of tools to explore tumor growth kinetics, but focuses primarily to describe single-cell dynamics and differential equations to simulate tumor volume changes during therapy and optimal control theory. Dr. Shagoke, it's great to have you with us today, and we're excited to listen to you. Most of us are familiar with modeling infectious diseases. So Dr. Shagoke is coming from the aspect of modeling non-infectious diseases. An example is what we have just described, tumor cases, cancer cases, and all the rest of them. So it's not all about infectious diseases. We also have that aspect of non-infectious diseases. And we can also model so many other things, just like my co-presenter said. So, but for today, let's listen to Dr. Shagoke. Dr. Shago, you're welcome. It's good to have you. You have the
Thank
floor.
you so much.
Please go ahead and teach us.
Can you hear me, please?
Yes, I can.
Yes, we hear you.
Thank you, sir. Thank you.
Yes, we can hear you, doctor.
Thanks so much,
Thank you
sir.
all. And I want to thank the previous speakers, Dr. Patrick, Dr. Josephine. Thank you. You guys are doing a great job. Today, without wasting much of our time, we'll be talking about like generally in mathematical oncology, how do we apply mathematics to cancer problem? So today I'll be talking about a mathematical model for estrogen paradox in breast cancer treatment. Several speakers, people are talking about more about infectious, and this one will also take us into another dimension. So the general outline for today is introduction, global view, predictive model, optimal control, breast cancer, related article, model formulation, results, and conclusion. We all know that the cancer generally, it's not infectious. How do we come across this? In a layman language, we have what we call normal cells. Every one of us have normal cells, and how does it happen? From where, from what angle? American Cancer 2023 says cancer refers to any one of a large number of diseases characterized by the development of abnormal cells that divide uncontrollably. That is, on the normal day, the cells in our body divided gradually when there is no alteration. And as you can see from here, we have what we call DNA mutation. But immediately there is a DNA mutation, that is, there is damage in DNA, you can see the way the cancer is being multiplied. So the more you multiply, the more they spread. So we have different ways, that's why up to now, we don't know what causes cancers. And globally, we believe we have a risk factor. We know that COVID is caused by this and malaria is this, but what causes cancer? So we only have a risk factor when it comes to cancer cases. So, for example, one of the risk factors is it might be hereditary, it might be radiation or chemical exposure, spontaneous error during the DNA duplication. It might be our environmental, it might be our way of lives. You see, that's why people believe that tobacco causes cancer. Some believe that alcohol causes cancer, different philosophy. But in this case, we will restrict ourselves into the risk factor. Now, what do we want to do? To kill or to control the cancer cells? But let's go on and see the global view of the cases. Globally, we know, globally, according to the Global Can, the cancers registry by WHO, we have 11.7% of breast cancer as at 2020. They do this thing interchangeably. But the problem we are facing in Africa is the data set. You can see each of the presentation, we keep on asking, how do you get the data? Where do you get this data? Because we know it's a problem. And that is why, as a mathematician and as an epidemiologist, anywhere you find yourself, let's try as much as possible to continue to spread the news of how people can freely, give some data out. We have a lot of data sets, but we don't use them. We have a lot of data sets, but we don't keep them. So these are the challenges we're facing in part of the world as a Black person. And look at this. We have lung cancer. It has the same thing. But other cancers also, we have other cancer. As a matter of fact, all the part of our body, there's no part that cannot have a cancer. So that's why we don't categorize this 42.9%. So in this case now, not only female that has the cancer, breast cancer, may also it's due to breast cancer. We have here 6.9. So in this case now, we have number of deaths here 6.9. But let's move on. I would like to show us this. In Africa, we have 5.7 incidents, both sexes, both male and female. So if you have 5.7, look at other region. Remember, we are still talking about the lack of data sets. And mortality for both sides, for Asian, for globally, we have this. And in the next 5 years prevalences, we have also 4.3 in Africa. But if you look at our population and look at the percentage, you can see we have a lot of stuff that we are talking about. But now let's look at, in this context, so today, in 2023 statistics now we're talking about, every minute we have 4 new cases and 1 death. Then every day we have 5,365. Then we have over 1,000 deaths. Then what about every month? What happened? Just to tell us that cancer is dangerous. And you can see from this graph, the trend is moving up, and you can see the female, here the female cancer, the breast cancer for female only, that's what the trend is taken here as at for the cancer cases. Now, we need to know all this background so that we should know that just to create appetite for us to know that we need a lot of people here also to do more cancer research. I'm not saying infectious diseases is not good, it's perfect. But now let's look at 2023 in breast cancer. As of 2023, according to American Cancer Society, we have male that has 2,800, and we have female that have close to 300,000. So, and look at the cancer, look at the breast cancer deaths too, it's also there. But that's not, having said all this, laid down all these statistics, there are, as a mathematician, what is my role to play? One of the things you need to play is this. I often hear people that say, oh, I love mathematics, but I don't like biology. There's no how, and you are in mathematical biology. So you just have to learn how to do this. First thing we need to do, according to the Rennet and Aiko, they said, number one, you must identify putative biomarker. Number two, you must develop mechanistic model. It's not necessary to be a bigger one. You must calibrate model with existing data, then validate the model with untrained data, and evaluate predictive performance for known treatments. Now, then simulate, predict untested optimal treatments. Now, let's go back to what is biomarker? Biomarker is, they are those things that come up when it comes to particular cancer cases. One of the biomarker for prostate cancer is PSA. We use PSA measurements to test the prostates, to know that this particular patient has prostate cancer. But in breast cancer, we call this one estrogen receptor alpha. Estrogen receptor alpha is one of those biomarkers that normally expose. Once they see the measurement, the oncologists know the sign of that estrogen, and they know when they can say, oh, this patient has the breast cancer. But unfortunately, majority of us in Africa, we don't normally dictate early stage. And that is one of the cry, and that's one of the announcements the WHO is making every day. It is better you do this. They are just go for mammogram and yourself also check yourself. If you notice any lumps, these are the things you can quickly talk about. But when it comes to, let's look at the pipeline that we are talking about when we are talking about the clinical aspect of it. Then in the clinical aspect of it, we have what we call clinical measured. That is when our statistical knowledge is being useful. And that's why, in cancer treatment, our body, the way you react is different. I can be given a particular, in the first cycle when I'm treating a patient, I can give a patient in first cycle, let's say I give them 2 doses, Orand, because of the nature of your own body, it might not be the same thing for the second patient. That is why in cancer, what they do is, the oncologists do most times, is patient-specific prediction. That is, you specify on those patients equally. You treat them accordingly, estimated. And let's move on because of our time. We can see that here, we have here the semantic. What are the things do I need? I need to set a clinical goal. I need to know disease-specific biology. I need to have what kind of data type do I need? If I said clinical goal is what factors are to be optimized: patient survival, disease progression, therapeutic efficacy, quality of life, and the side effect. Because you have to check the side effects of chemotherapy you are using, or radiation, or any type of treatment you want to embark on. Then these are the way we gathered the data. And treatment resistance. At what point do you have a resistance in the body, immune response, drug mechanism in the patient? And then on the data aspects, what is the volume of the tumor cell at the point whereby I'm measuring them? And when I begin to treat them, at what point is this tumor shrinking, or is it spreading to another places? So these are the things we check and we notice, and that help us to be able to use our mathematical skill to be able to write the equation out. Then mathematical representation, ODE, PDE, or ABM, which is agent-based model. I was listening to the previous speaker when she was telling us about agent-based model. We use a lot of agent-based model in cancer problem. Agent-based model, we have a lot of code already written. We have a lot of software that works along with mathematical equation. They are mathematically inclined to. So we have treatment dose, we have toxicity, you have to measure toxicity of that in the patient. So now, let's proceed. For today, we will, like I told us, we'll be talking about estrogen paradox. The aim is just to investigate the possible trade-off between the tumor suppressor protein P53 and estrogen receptor alpha that leads to breast cancer elimination. So if you look at this diagram, we are talking here about the normal cell and the way it grows, and the abnormal cells. The breast cancer can be as big as you can see here on your screen. We have it in this case as big as this. And this is one of the biggest tumor in the world. It was operated and it was removed sometimes ago. So here we have this. I have some related article that talks about different type of cancers, and the one I was telling us the other time about specific patient. If you look at this particular is a prostate-specific antigen, which is PSA, dynamic predicts individual response to intermittent androgen deprivation by Renard and et al. So we have different set of data sets. As a matter of fact, in this particular paper, they collected the data set for almost 3 years in a clinical setting. And those particular patients, they measured the dates, the dose, the hours they are giving them. And they are now looking at the response of the treatment. So they are able to predict what really happened to each of them. Some of them are slowly increasing. Some of them are rapidly increasing. Their immune system continue to grow. And some of them, the PSA begin to reduce. So one after the other when they treated the patient. So in this case now, we are back to our own model. In our own model, we have what we call tumor, dormant tumor, and we have active tumor. We have also estrogen compartment, and we have P53, which is protein. So this diagram is just a semantic aspect of this work. But as you can see from the first, one of the things is tumor proliferation. How do they multiply? And we have the carrying capacity, also KD. And here, our alpha here is representing activation of dormant cancer cell. Then the second compartment, we have activation of dormant cancer cell and tumor proliferation. It's moved from here, and naturally, cancer also died natural death. We call it apoptosis. Apoptosis, it can undergo apoptosis, and at this point, we have estrogen, we have supply of estrogen. This is a natural estrogen and deregulation. But at this point, we have what we call P53. P53, what's the work of P53 in our body? It's just to suppress the tumor growth. It's a growth that normally work against the tumor development in, it's a protein that normally work against tumor growth. But in another way, remember those tumor, what we call tumor today, they are the one that grow abnormally. They can overpower it. Immediately they overpower it, that is when we now comes in. Now, what are the things we want to check here? We want to see how can we introduce the what we call estrogen, high dose of estrogen, in order to treat this particular cancer. So we move on into the analysis. On the analysis, we were able to justify some. We don't have data here. It's all about the literature, those are data that are in literature, especially their clinical data in the literature. That's what we invested and that we used to justify the dose here of this particular dose we are talking about. So from here, we are able to establish the model was well posed. I don't need to show us all this, integrating the mathematical analysis, those one because of our time. So we're able to have some few results. We're able to establish the global stability analysis that we have this. And the lemma says, don't forget your alpha. Our alpha here is activation of dormant cancer cell. So we are able to establish this global stability and global asymptotically stable. And anymore at this point, we are talking about alpha naught less than RD. Our RD is the growth rate of dormant cancer cell. Anytime alpha naught is less than that, what happened? It simply means the system is globally asymptotically stable. And when we have alpha naught greater than RD, which is our growth rate of dormant cell, is globally asymptotically also stable. At your dormant cell is 0, active cell is 0, and we are at this particular equilibrium point. So the paradox aspect, the interpretation of it is, number one, we need to avoid activation dormant cancer cell. The level of estrogen should be small enough so that at any time you are using what we call high dose of estrogen, we need to be able to control it. And another thing is the tumor will be activated, subsequently will grow to reach a non-zero equilibrium point. So all these we have them in the result, and the result is also published. Myself and my mentor during my postdoctoral study in the University of Pretoria in South Africa, then Professor Rashid Ufiki. And we have some nice preposition results. But now let's look at this particular illustration, the simulation we have here. So at this point, we depict the temporal evolution of dormant and active cancer cell. That is, if we have lambda E, our lambda E is the source of estrogen, is equals to 60 days. If it is equals to 60 days, and the source of protein is 5. What happened? What is the nature of this graph? You can see that it indicates the system converge to a dormant tumor endemic. an active tumor endemic equilibrium confirmed from our results. So we have a lot of different results in this case that we need to also showcase. But because of our time, we will also move on. And here we also look at the point whereby our days, our P is still 5, and we increase particular day, we are looking at it. And at the end of the day, you see that our tumor-free is also converged, and active tumor-free equilibrium confirmed from the results. But the only thing we need to establish here is the other part of it. Now let's look at this. Active tumor cells are eliminated in the green area. So if you look at all this green area, that is when we are able to manage to eliminate the active tumor cells and persist on the red one. The figure shows the estrogen paradox and its paradoxically long-time effects. Now, if we are using, we all know that cancer cell, one of the things that cause the cancer cell is what we call excess estrogen. And now the medical came up with estrogen high dose. They said if you use estrogen high dose, but in our simulation, we are able to confirm that if you use estrogen high dose, it can only contain for a particular period of years. After that years, the cancer reoccurrence will occur. So these are the things these results were able to show us in the long. Now, in conclusion, let's look at it. The breast cancer occurrence may result from a rise in estrogen level or drop in P53 level. Successful elimination of breast cancer may be achieved by anti-estrogen drug or by using high dose of estrogen. Then another thing is that the breast cancer reoccurrence could be caused by the further raising the estrogen level or by dropping the P53 level. So finally, we provide explicit condition under which the paradoxical cancer reoccurrence that emerges from prolonged HDE. HDE is high dose of estrogen. So all these things are treated, and for example, one of the things you have to be careful with when you are formulating the model, always remember you are not doing infectious diseases. So because it's not that hoggle like the way we normally use infectious diseases. So thank you so much for listening. And because of our time, I would like to stop here. Then to appreciate one of my my mentor, Professor Rashid Ofiki, and with other people that we also work together in this case. Thank you.
Wow. Thank you, Dr. Shegun. Thank you, thank you, thank you. This has been eye-opening. This has been enlightening, especially for me, and I think for some other people. It was nice listening to you. This is one area that I have not ventured into. And now I can begin to appreciate the agent-based modeling thing that Dr. Josephine was talking about, where you have to treat an individual's case based on that individual's peculiarities. So I can begin to understand that agent-based modeling, where you don't just have to lump them into compartments, based on how they move from one stage of the disease to the other. All right, so quickly, we have run, far out of time, but let's just take a few questions. For those who might have questions, you just simply raise your hand. Let's just do that in 5 minutes. Raise your hands if you have any question, and then you'll be called to speak, or you can type in the chat box if you have a question to ask. So any questions from anybody? I'm sure most of us have not ventured into non-infectious disease modeling. So this is good. As well, a lot of people are still trying to digest what you've said. But it was a nice, enlightenment. So any questions from us? Any questions? Let's see the hands of those who have questions to ask. We don't have questions. Dr. Danso, are you there?
Yes,
I
I'm
can
right
see
there.
one hand.
Your hand is
Okay.
up now.
Okay, one hand is up. Tijani Kazim Austin.
Yes, ma'am.
Okay, please go ahead and ask your question. Unmute yourself.
Okay. Lecture. So what I don't understand is in this kind of area, is it that you don't consider reproduction number since it's not like an infectious disease?
Yes, it's in most cases. Now, I'll share my experience with you.
Okay, sir.
We consider at times. It depends on the nature of the cases you are treating. It depends on the aspect you are considering. Remember, we are talking about secondary infection in reproduction number. And in this case now, it is not all about infection. It is all about spread. So to capture it in a majority of us, we don't look at, remember in a compartment, you can easily look at reproduction number. But when it comes to cancer cases, it's all about individual. That if I want to treat this patient, first thing that comes to my mind is, how does it react? Remember, there's this thing we call a PKPD model that is going on now. In PKPD model, that is pharmacokinetic and pharmacodynamic. How does the body react to this drug? And how does the drug react to this body? So these are the things that we normally see in cancer cases. That's why the issue of reproduction number is less considered in that manner. But we always like, then if anybody want to collaborate with any oncologist or any medical people, there are different things we need to consider. Number one, which type of data do you want to get from them? There's a difference between clinical data and medical record. Don't go for medical record. There are medical records, they have no impact in the patient. Their demographic record, they have no impact in their own. Although people in the field might be using them for a particular reason, but for us to touch that particular life, in America here, what they do is we have what we call a tumor board. On the tumor board, it simply means as a mathematician, you have a place. As a statistician, you have a place. As a physicist, you have a place on the board on a particular patient. You might be 25 of you, it might be more than that have a say on a particular patient, so that they also will bring their own experts onto the field and people without reason together for them to be able to be treated. So these are the things they do. Although I was told in Nigeria or in other parts of the world too, they have something similar, but they might not have the entire world, because some of us don't believe, majority of them don't believe in mathematics. And these are the things we are using these days to help to share more light into the cancer problem. Thank you. I hope I've managed to answer your question.
Mr. Tijani, I hope your question was answered. I was also kind of expecting that question about the reproduction number. I was also kind of expecting it. You don't have to find R naught and then start doing some analysis of it. All right, so any other questions? Today, mathematics has indeed met biology. So we have seen infectious diseases and non-infectious diseases. Ms. Ataribu Samuel, please go ahead. 1 minute. We are behind schedule. 1 minute. Mr. Ataribu Samuel, please.
Thank you very much.
Okay, is there any way with stability? How do we measure the situation when we're trying to address the cancer in the lab? How do we use mathematics for stability level? Maybe in terms of treatment and response.
Now, how to do that in lab is there are many ways of doing that. Number one, we have some lab that they normally have what we call, they use rats, rabbits to perform their experiments. Remember, those scientists believe that you can get those data and you can even formulate simple model. You don't need to complicate the model like we do in infectious disease. You know, in infectious diseases, we consider different scenario, but when it comes to cancer problem, you only focus how big is this, what is the response? Because there are way of measuring the response. They are the one to do that. You are a mathematician, don't forget. They are the one to do all those practical and give you the data. And those data will not be the one you will use to be able to make some contribution to what they are doing. Number one, they know how to culture the cells. They know how to put some certain thing into the cell. Those things, the way it grows, they know how to give them the medication. They know how to measure what is going on among those rats or mouse or they are using. So once they can get those data, then you can now come in and say, okay, what is the carrying capacity? What are we studying? That's why we need to, first of all, like I told you in this particular, you need to first of all look at what we call, go back to the model. How do we model the cancer itself? That's why you have to go back to that particular model. So if you look at this, let me just try and go back to this. So this will help us in our day-to-day activities. Just a minute. I'm just trying to, okay. Can you see my screen now? Can you see my screen, please?
Yes.
Yeah.
Yes, please.
So if you can follow this rule, this particular treatment, look at this. Look at this for optimal treatments now. Treatment order, treatment schedule. If they are given the mouse, how many doses are they giving them? What type of treatment are they using? Are they using infusion? Are they using tablets? How do they pass this treatment into their body? These are the things that will help our model formulation. That's why you need to know this disease-specific biology. You need to know, which cancer are we talking about? Are you talking about skin cancer? Are you talking about prostate cancer, breast cancer, lung cancer, different type of cancer we have? You have to first of all read about them. Then these are the data you can imagine. Imaging data, you can get it. The volume, how big is this tumor? When we use it yesterday, how big? You measure it. When they use it today, next day, like that, they continue to measure them. So these are the things that will help our model, and just a simple model, and you'll be able to personalize it. Thank you.
All right, thank you, Dr. Shegun. I think that will be all for today as regards questions. And in general, Dr. Datsu, are you there?
Yes, I am.
Okay, so I think we can just quickly take the general interactions. I can just do that in 5 minutes.
Yes.
So I'll be out of here in another 5 minutes.
Well, okay.
We're
I think
supposed to have ended by 7. This is 20 minutes past that.
Yeah, we are
so
sincerely
generally
sorry for that. Please
All
go
right,
ahead.
so
Sorry.
thank you our speakers. Yeah, thank you our speakers, Dr. Patrick, Dr. Josephine, Dr. Shegun. Thank you for finding time in your very busy schedule to interact with us, to teach us, to enlighten us, to get us thinking and imaginative and creative, so we can go ahead and break barriers in different fronts. Thank you for your time, and thank you to all the participants and the attendees for listening and spending time with us. Today we discussed, the applications of mathematics in the field of biology, both for the infectious diseases and non-infectious diseases, and general modeling of epidemiological cases. And this is just webinar we're having for this quarter. That's the BMA is having for the year. So we're going to be having 4 in a year, and this is the first. So we're expecting 3 more before the year runs out. By the second quarter, that will be sometime in May, we are going to be looking at the application of math in technology. We're going to be looking at applications of linear algebra, topology, calculus, and statistics in technology. And by the third quarter, we are going to look at financial mathematics, that's math and money, actuarial sciences, and investment. And by the last quarter, we are looking at sociology and population dynamics. I saw someone in the chat asking, okay, if we're going to be looking at fluid dynamics and combustion. That's an area we also consider. So it would be nice to hear or have your input on things you want us to bring across your way in BMA. That's what we are here for. We're here to learn, encourage one another, share experience, share knowledge, help each and every one of us to grow. So if there are things you'd want to learn or understand as regards one thing or the other, collaborations and all that, that is what BMA is all about. So you can just be dropping your suggestions. We are taking note of each and every one of them, and we are going to act on them. So feel free to stay with us and keep interacting with us. That's what BMA is all about. So thank you for your time. I'll hand over to Dr. Dansu to formally close us and give us any parting words or shots. Thank you.
Yeah, thank you so much. We appreciate all our speakers once again. Dr. Patrick Jomeni, Dr. Justin Tete, and Dr. Shego. Okay. We are very grateful for all the very insightful talks, and I know that one or two people have been inspired here. I got some requests about probably having the slides. So if our speakers don't mind, you could send us the slides later so we can circulate to all our participants. If you don't mind, that's if you're comfortable to share with us. So before we close, I have a couple of announcements. Okay, I've talked about the request for slides. And of course, for those who did not get the full gist, who were not around throughout, like I announced earlier, we are going to, once the recording is completed, we are going to put it on YouTube and share the link with everybody who registered. And for those who need certificate of participation, please send your name and affiliation to blackinmathematics@gmail.com. So if you sent your information in the chat earlier, that does not count. You may not get your certificate. So, but if you really want a certificate, please send your information to blackinmathematics@gmail.com. If you'd like to join Black in Math Association, I think we got a request like that. You have the link right there in the chat now. Just click on our website and then you'll find your way there. Then Dr. Patrick Yomeni actually told us about African Mathematical School of Mathematical Modeling in Biology that is coming up, I think, March 20 to 28 or so. And there, the focus is on data collection, data fitting, and all that. So you have the link also. I've posted it in the chat right now. You can just click on it and register. I know this is going to be very helpful. And Dr. Nick already announced all the webinars we have for this year. So the next webinar will be our second quarterly webinar, which comes on by Saturday, 6th May 2023. And the focus is on math. The theme is math and tech, and we're focusing on applications of the mathematics relevant tech in summary. So as we go, can you just do something? Just give your favorite emoji to the speakers in appreciation to them. We appreciate all participants, members of Black in Math Association. We appreciate you who are here. We also have in attendance our partners, the South African Mathematical Society, I think I see a couple of people around from France. Thank you very much for being part of us here. Everybody who came from everywhere, we are very grateful to have you. Our speakers, once more, we are very, very, very grateful. And we know that when next we call on you, you'll oblige us. So we'll continue to engage you via email. Dr.
If our
Nika,
speakers don't mind, if they want to say, something to us, a parting shot in 1 minute, if any of the speakers want to say something in a minute or two, please.
Yes.
Dr. Josephine, Dr. Shegu, Dr. Patrick, if you'd like to say something in a minute or two, please go ahead. Dr. Shegu.
Yeah.
I saw your
Okay,
lovely
I
emoji.
just
Just
want
say
to
something to us before you go.
thank you so much. Thank you for the opportunity. Thank you for every one of us that tried to make it today. Let's just keep on pushing ourselves. Let's keep on learning new things. Let's continue to encourage ourselves. The fact still remains that out there, being a Black alone is a disadvantage to some of us, but we thank God that we are still making Black race too popular, and we are making impact, and will continue to make impact. So the only thing we can do just to help one another is just that you don't need to hide that code. You don't need to hide it. Share it with people. You don't need to hide the model. You don't need to hide the data. Share it. That is what make all these people that we are seeing up. That is what make them, triumphant. So let's try as much as possible, share the material among ourselves. When people send you email, please don't ignore them. Listen to them, hear them out. If you can help, help. If you cannot help, look for someone else that you think it can help the same person in the same Black community. Please, let's try as much as possible. We are not more, like somebody used to tell me, he said, we are not more than this. Why can't we help ourselves? So let's help one another. So far you are a Black. Sincerely, we are going somewhere. And we can only go somewhere when we take ourselves along. When you hear information, don't hide that information. That does not mean your own will not come. Share the information. Thank you so much. Over to you.
Thank you very much, Dr. Shegu. In fact, what you said is like the summary of everything. Share, and collaborate. Share, and collaborate. That's just it. That's how we rise, by lifting everyone at the same time.
From my interaction with him is that when you are writing a paper, look for paper by a Black person, cite it. That is one of the ways to help ourselves.
That's another one, yes.
Cite. You definitely find a relevance for no matter what. So I think that's so helpful. Thank you so much.
Dr. Josephine, do you want to say something to us? Dr. Josephine.
I just posted my thank you to everyone in the chat. So really, I was glad to be a part of this, and I hope next time, your next quarterly meeting, I will be a part of it, and to be as interesting as it was today. Thank you.
Thank you.
Thank you very much. Thank you. All right, Dr. Dansu, over to you. I think we can just close.
You still have Dr. Patrick? Patrick, you want to say
Dr.
something?
Patrick, I can't find him in the room. I don't know, is he still with us?
Okay. Okay.
I can't find him in the room. I think he has gone off.
By 30 minutes, and we sincerely apologize.
Yes, we have.
Of course, you agree with me. It's been so impactful. Thank you so much. We hope to see you again 6th May 2023 as we look at maths in tech. Thank you once again, our speakers. Have a great time, everybody. Yeah.
Have a good evening.
Oh.